Hello, and welcome to this lesson where we're going to develop the solution to one of our recent assignments, which was to develop a 5 to 32 line decoder. In this lesson, we're going to go from top to bottom. We'll start by designing it on paper, then do the Verilog, then do the test benches to verify our output. So let's just get into it. This assignment asked us to develop a 5 to 32 line decoder. Let's start with what we know from our previous lesson about decoders. So we're going to build this guy. It's 5 to 32 decoder. And all we really know about him at this point is that he's got an output D, that's 32 bits, and he's got an input A, that's 5 bits. And we know how decoders are composed of smaller and smaller decoders. So in this case, our K is equal to 5, which is an odd number. So this decoder is going to have two decoders that are K plus 1 over 2 and K minus 1 over 2. So 5 plus 1 over 2 is equal to 6 over 2 is equal to 3. So from this one, we know we're going to have a 3 to 8 line decoder. And over here, with K minus 1 over 2, we've got 5 minus 1 over 2 is equal to 4 over 2 is equal to 2. So we've got a 2 to 4 decoder. So now we've got a lower level of abstraction for our design. We know that we're going to still start with A, that's 5 bits, but now we know that we're going to have a 3 to 8, and a 2 to 4. And the input lines here will break out. So that's going to be A0, A1, A2, A3, and A4, just like that. 6, 7, 8 outputs from the 3 to 8, and 4 outputs from the 2 to 4. So that means we're going to have a total of what? 8, 9, 10, 11, 12. So the wire in this case is going to be equal to 12 bits. And then we'll have 32 AND gates. And this one will be wire 0, 6, and wire 7. So 0, 1, 2, 3, 4, 5, 6, 7. Oh, not. This will be wire 8. And this one will be wire 0, and this one will be wire 9. And this one will be wire 0, and this one will be wire 10, all the way down until we get wire 8 and wire 12. Oh, look, I screwed that up again. Not wire 8, it's going to be wire 7. And then all of those, well, and then each of those are our output D. So that's going to be D sub 0, D sub 1, D sub 2, all the way down to D sub 31. So at a high level, that's going to be our design. We've got inputs that are 5 bits, our 4-bit output. We have 12 bits of wire to carry our signals from our decoders to our AND gates. And then we've got 32 total AND gates, 0 through 31. But we're not done designing yet. Remember, now we need to create a 3 to 8 and a 2 to 4. So let's go ahead and do the 3 to 8 first. Now the 3 to 8 has k equals 3, which is also odd. So we'll also have a k plus 1 over 2 and a k minus 1 over 2. So k plus 1 over 2 is going to be 3 plus 1 over 2 is equal to 4 over 2 is equal to 2. So the 3 to 8 will have a 2 to 4. And k minus 1, 3 minus 1 over 2 is equal to 2 over 2 is equal to 1. So it's going to have a 1 to 2 decoder down there. So a 2 to 4 and a 1 to 2. So now let's just take a look at our input side. On the inputs, we're going to have A, which is going to be 3 bits. We'll then have a 2 to 4. And a 1 to 2. So let's see. So we've got 2 inputs going to A. That'll be a 0 and a 1. And we have 1 input going to the 1 to 2. That'll be a sub 2. 4 coming out of the 2 to 4 and 2 coming out of the 8 to 2. That means we're going to need wires that are 6 bits. So this will be wire 0, wire 1, wire 2, wire 3, wire 4, and wire 5. And then we'll need 8 AND gates. And the first one will be wire 0 and wire 4. Then we'll have wire 0 and wire 5, and then wire 1 and wire 4 and wire 1 and wire 5. Remember, the goal is to just get every possible combination of the outputs, wire 5 all the way down until we have wire 3 and wire 5. And these will be our outputs, D0, D1, all the way down to D sub 7. So there's our 3 to 8 decoder. 3 bits of input, a 2 to 4 decoder, a 1 to 2 decoder, a 6-bit wire to carry our signals to our AND gates, and then 8 bits of output. Remember, each AND gate takes every possible combination of the wires. So let's see. Now we need to go ahead and do our 2 to 4 because all of these designs require a 2 to 4, and then we'll make a 1 to 4. So now let's do the 2 to 4. So in this case, k is equal to 2, and that's even. So we'll just have 2 times k over 2. So that's 2 over 2. That's 1. So this design is going to have 2 1 to 2 decoders. So let's see. On the input side, we've got A, which in this case is going to be 2 bits. We'll have 2 1 to 2, 1 to 2. First one will get a 0. The second one will get a 1. They each produce 2 bits of output, so we'll need 4 bits of wire. So that'll be W0, W1, W2, W3. And then we'll need 4 AND gates. We can actually draw all these this time. And that'll be W0, W2, W0, W3, W1, W2, and W1, W3. And these are our outputs, D sub 3, D sub 2, D sub 1, and D sub 0. And there we go. There's our 2 to 4 decoder, right? The pattern is the same. Now we just have 4 bits of wire going out to our 4 AND gates. Now, the last thing we need is that 1 to 2 decoder. And a 1 to 2 decoder is the smallest flavor of decoder, right? It only has 1 input and 2 outputs. So no K calculations necessary. A is 1 bit. It splits to a NOT gate. And we get our outputs, D sub 0 and D sub 1. So there's our 1 to 2 decoder. So now we've done everything that we need to do. We have a 1 to 2, a 2 to 4. We used a 1 to 2 and a 2 to 4 to make a 3 to 8. Then we have a 2 to 4 and a 3 to 8 to make a 5 to 32. So we're ready to start at the bottom and build our way up with the Verilog. So let's switch gears and let's switch over to Visual Studio Code. Let's see. I've created a folder that I call on the desktop. It's called Decoders, and I've got our starter file in there. And I'm going to go over to Visual Studio Code, where I've got the file opened. Right, all I did was go File, Open Folder, go to my desktop, grab Decoders, open it up, and now I've got this. So, just to kind of keep it with what you guys were expected to do, I'll rename the starter file. This is not my real R number, just whatever that is, some random numbers. And there we go. Let's go ahead and change that there at the top. R, what did I put? 2. This would be like an R number in 10 years. 4729847.v. I'm going to leave the top module the same. Oh, I do need to add a semicolon there. And then we'll get ready to add our Verilog, except we're not ready to add it in our top module. We need to create those smaller Verilog modules so that we can slowly build up over time. So let's actually start with our 1 to 2 decoder. So I'm going to create a module. I'm going to call it Decoder 1 to 2. It's going to have inputs A and D. End module. It's got an input A that's 1 bit, an output that is 2 bits, so 1 to 0 to make it 2 bits, D. And we just have that D sub 0 is equal to, actually we're going to flip it over because we want the, we can do it this way, it's okay. It doesn't really matter. D sub 0 is equal to not A, and D sub 1 is equal to A. And there is our, except we forgot our assign and assign. So there we go, we're making sure to save our file. Now, here's the important part. A lot of people will work all the way to the end and then start testing their decoder. It is very, very important that you test right away. So we're going to make a test bench for just this Decoder 1 to 2 module. So I'll go over here, I'll click New File. I'll call this Decoder 1 to 2 underscore tb.v. And now we've got to add all of the rest of our stuff. Timescale, 1 nanosecond, 1 nanosecond. Include, this is where I'm going to regret putting this random number in, 294729847.v. And let's make our module. Module Decoder 1 to 2 underscore tb, not .v, underscore tb, in module. We'll create a reg for A, wire that's 2 bits for D. Now we need to create the module. This is what we call instantiating our module. So we're making a decoder 1 to 2. It's got inputs A and D, so we create decoder 1 to 2, A and D. Now the reason we don't have to do this .a business, while this syntax would work, if the variables are named the same thing and are the same size, you can actually just drop in the same symbols and it will work just fine. So decoder 1 to 2, UUT for unit under test, and this is just our UUT is just our identifier. And let's do the thing. Initial, begin, and end. We need to create our files to dump things in. Dump file, decoder 1 to 2 .vcd. Dump vars 0 from decoder 1 to 2 underscore TB. And let's do this stuff. Let's see, we need to make A equal 1 bit 0 and delay for 20, and A equal to 1 bit 1. And let's also delay for 20. Remember to save. So now I'm going to switch over to PowerShell. And let's go cd desktop, find a file, cd decoders, all our stuff there, make sure our files exist. And so now let's go ahead and do I verilog.o decoder 1 to 2 .vvp decoder 1 to 2 underscore tb.v. Hey, look at that, we got errors. Let's take a look and see what we've got. Oh, it did not like that we have this empty top module. Let's go ahead and delete, or let's comment that out for now since we're not using it. And let's go back, let's try that again. There we go. So it got mad that we had a top module that had no stuff in it. So when the synthesizer went to go see what was happening, stuff got weird. So here we go, VVP to run the simulation. Decoder 1 to 2 .vvp. There we go. Now we do GTK wave. Bring it over here. File, open new tab. Get that VCD file. Grab our signals, hit append. And then let's see. So there's been some confusion about what to do here. So we've got the output going from 0. So when A is 0, we've got 0, 1. And when A is 1, we've got 1, 0. Now this is technically correct. We just have it going in a different order. We have it going from least significant bit to most significant bit. But by convention, we kind of want to go the other way around. So what I'm going to do is go back to Verilog. Go back to Verilog, and I'm actually going to flip this over. We'll start going from ascending to top. So what that means is if we go back to our design here, it just means that we're going to flip things over, and we'll have, get my draw tools, we'll go D0, instead of D0 to D1, we'll go from D1 to D0. So we'll go in descending order of our outputs. So here in the, we did that here, 3, 2, 1, 0, all the way down. Here we did this one backwards. And the important thing here is that it's okay to screw stuff up, right? It's important to be able to kind of go back and see what mistakes you made and think critically about what the behavior is and what does it mean for your circuit. See, we want to flip this one over here, and we want to start at 31, 30, 29, all the way down to D0, right? So you want to think critically about what's happening and what you're working with, and be able to go back and look at your design and make changes. So we've done that. Now let's go back to the PowerShell. Start at the very top again. Run that. BBP. We get GTK wave again. And we'll go to File, open new tab, get the .vcd file, get our signals, append them, and now it's the output that I want. When A is 0, D is 1, 0, and when A is 1, D is 0, 1. So that signal is walking from left to right, or the 1 is sort of walking from left to right, from most significant bit to least significant bit. So from this test, we can see that our 1 to 2 decoder is working. So now it's time to make the 2 to 4 decoder. So let's do that. 2 to 4 decoder. Module decoder 2 to 4. It's also going to have inputs A and D. But this time the inputs, like we saw before, are equal to our 2 bits in length. So we want to do 1 and 2, and our output is 4 bits, so we want to go 3 to 0, D. And then remember from our design, we are going to need, let's go back down to the 2 to 4, 4 bits of wire to connect Y0, 1, 2, and 3 to connect to these AND gates. So we'll need to create a wire that is 4 bits, 3 to 0, and we'll just call it W. Now we need to do the module instantiations, right? This is where we actually drop in the other decoders. So what's going to happen here is we're going to go decoder 1 to 2. I'm going to identify this one as U0 for unit 0, open parentheses. Dot A is just going to attach to A sub 1, and its D is going to attach to wires. Let's go 3 to 2. We'll do everything in ascending order and see if that looks good when we're done. All right, I haven't worked this out ahead of time, so we're kind of doing it live, and we're going to do a little debugging as we go along, which I think is a beneficial experience as well. So we had .A, so the 1-bit input A for the 1 to 2 decoder, we're attaching it to the 0th bit of A from our 2-bit input, and D, the 2 bits of D, will attach to W. We've already used 3 and 2, so now we'll do 1 and 0. So that's our module instantiations. Now time for our AND gates. So we'll assign D sub 3, and we're going to start with ascending order, is equal to W3 and W1. So that's the most significant bit of the first decoder and the most significant bit of the second decoder. And then we'll assign D sub 2 attached to W3 and W0. Assign D1 is equal to wire. So now we've done wire 3 both times, so we'll do wire 2 and wire 1. Assign D0, the last one, is equal to wire 2 and wire 0. So here we can see that hopefully we've covered all of the output combinations from each of our internal decoder modules. Now we need to test this decoder. So we're going to make a new test bench. We're going to test it every step. So this is going to be decoder 2 to 4 underscore TB dot V. Now I'm going to go to my other test bench and I'm going to copy and paste all of this since we're only going to make some superficial changes. So I copy and pasted that. Now this is module from 1 to 2. We're changing this to 2 to 4. Our input registers are now 2 bits. Our output wires are now 4 bits, so change that to 3 to 0. We should be testing decoder 2 to 4. We also want to change the file output to 2 to 4.vcd, and we want to get our variables from decoder 2 to 4 underscore TB. Now we do need to change this bit up. A is still just our input, so A is a 2-bit number. A is equal to now to 2 bits Let's stay in binary because it's small. 0, 1. And let's delay for 20. We know that we have 4 possible input combinations, so I'm just going to copy and paste it 3 other times. I'm going to change that to 0, 0, 0, 1, 1, 0, and 1, 1. So now that we've got every possible input combination covered. So that's all we need to do for our test bench for our 2 to 4. Now let's go and see if it actually does the thing. We don't need one node right now. Let's clear this. Verilog -o decoder 2 to 4 .vvp from decoder 2 to 4 underscore tb dot v. Hey, look at that, we got some syntax errors. So to see, in our module on 23, we have a syntax error. 23, error invalid port connection expression. So it says lines 23 and 24, we screwed something up. So let's go ahead and take a look and see what we did. So yeah, that's our module instantiations. And what did we mess up? Look at that, we forgot our parentheses at A, right? We should have closing parentheses there and there. Do I have an extra parentheses that I don't need then? Yeah, I do. So, the take home there, let's recap what just happened, right? We ran the decoder, we looked and said, all right, we got syntax errors. We see that it's in our R-numbered V file, line 23. Something about our port connection was messed up in our module instantiation, and same thing at line 24. So we know to go over here and look at 23 and 24 to see what we screwed up. And we noticed that we had a missing closing semicolon. Or actually, it was a misplaced closing semicolon. It was down there at the end of the expression, not at the beginning like it should have been. So let's run the simulation again, or try to synthesize the code now. That seemed to work. Now let's run the simulator. VVP decoder 224.vvp. Look at that, it created our .vcd file. So let's go to GTK wave. Bring it into the mix. Open our tabs. Let's grab our decoder 2to4.vcd. Let's check these signals. And look at that. So we've got 8, 4, 2, and 1, which we know is in binary, but it would be helpful if we can actually see it. So if I go over here and right click on this guy, hit data format, and say binary, look at that, it'll show me the binary. So 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So we've got that input walking from left to right like we want. So we know now that our decoder, our 2 to 4 decoder, is working properly. So that's good. We can move on. So let's close GTK wave, let's minimize that. And now we are ready to build our 3 to 8 decoder. So module decoder 3 to 8. It's also got inputs A and D in module. Helps if you spell it correctly. Let's take a look back at our notes here. If we scroll up, where's my 3 to 8 at? Yeah, okay. So it's got it's right here. It's got a 2 to 4, a 1 and 2. It's got 3 bits of input. It's got 8 bits of output. And the wire, this is what I was interested in, is 6 bits. So we've got 6 bits of wire. And remember, from our notes here, we're going to flip everything over, and we're going to go from 5 down to 0 to keep everything in descending order. So that means we have inputs, 3 bits, so that's 2 to 0, A. Output, 8 bits is 7 to 0, D. And then a wire that's 6 bits, so that's 5 to 0, W. Now time for our module instantiations. So the first thing we need is a 2 to 4. So decoder 2 to 4, call that guy U0. Its A is going to be connected to our A, but we're going to connect it to 2 and 1. And our outputs, .D, we're going to connect to wire, starting at the top, take the first 4, so 5, 5, 4, 3, 2. So 4, 5 down to 2. That seems to make sense. Let's make sure we have all of our parentheses like we need. So that's our 2 to 4 instantiation. Then decoder, we need our, what are we making now? The 1 to 2. Call that U1. Its input, since we've already used 2 and 1, all we have left is a 0. And its D, its output, is connected to wire 1 to 0. And that should be properly connected. Can use some tabs to make everything line up all nice and pretty. Now the AND gates. So now we're going to assign, starting with D7. So that's going to connect to, here's where it gets interesting. Remember, we just started at the top of each decoder. So we're going to start with wire 5 and wire 1. So wire 5 is the top output of the first decoder. Wire 1 is the top output of the second decoder. And we got assign D6 equals wire 5 and wire 0. So now we know it's just going to repeat for wires 4, 3, and 2. So I'm actually just going to copy and paste this and go 4, 3, 2. The D's need to descend, so 5, 4, 3, 2, 1, 0. And every second one here, we need to go 4, 1, 4, 0, 3 and 1, 3 and 0, 2 and 1, and 2 and 0. So a little bit of copy paste action just to kind of speed up our development just a little bit. And that is it for the 3 to 8 decoder. Let's make the test bench. So let's go and grab all of this code again. I'm going to create a new file. I'm going to type it decoder 328 underscore tb dot v. Paste in some of that stuff. Change the names up here. This would be 3, 2. Oh, this one I can be smarter. Always work smarter, not harder. So I'm going to change. Anytime I see 1 to 2, or no, excuse me, 2 to 4, I'm going to replace it with 3 to 8. And replace all. There we go. Working smart. Now, the last thing we need to do is create our A, which is now a 3-bit binary. Let's keep it in binary. This probably will be the last one we keep in binary. So A00, delay for 20, and then we'll copy and paste 1, 2, 3, 4, 5, 6, 7. And we'll go and fix the binary. 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And there is our test bench for the 3 to 8 decoder. So let's bring back PowerShell. Clear out the old stuff. Verilog, option O, decoder 328 dot VVP. We want to create it from decoder 328 underscore TB dot V. Now look at that, we screwed some more stuff up. 3 to 8, oh, this one is messed up in the test bench. Oh, I understand. So let's take a look at this. I think I had no idea what I screwed up when I did my copy paste, but let's read the error. So it says decoder 3 to 8 at 9, warning, port 1 of decoder 3 to 8 expects 3 bits. So port A, the input of decoder 3 to 8, expected 3 bits, but got 2 bits instead. Decoder 3 bits, so at line 9 again, D, expected 8 bits, got 4. So this tells me that I forgot to update the inputs. So it says right here, A should have been 3 bits, it was 2, D should have been 8 bits, it was 4. Now notice too, it just says warning, not error. It actually still created the .vvp file. It just padded the extra bits with extra zeros. to make it work, but it let you know and said, hey, this is probably messed up. So like all programming, it's usually a good idea to treat warnings as errors, even though the system will still let you run. So let's go back and fix it. Yeah, as we expected, A needs to be 3 bits, so that should be 2 to 0, and D should be 8 bits, so that should be 7 to 0. Let's try again. Look at that, completed with no errors and no warnings. Now VVP decoder 3 to 8 dot VVP, created the dump file, GTK wave, should come up with a better name than dump file. File, open new tab, go hunting for decoder 3 to 8 dot VCD, open it up, let's grab our signals, and now notice it's given to us in hex. So 8040201008040201. So if you remember your hexadecimals, this is what we expected, but let's go ahead and see it in binary just to make sure. Binary. And yeah, when we flip it over to binary, we can see the 1 sort of walking across from most significant bit to least significant bit. So we know our 3 to 8 decoder is working properly. So now it's time. We've done the 1 to 2. We've done the 2 to 4. It is now time to do the 3 to 8. So we've got some options here. Let's go ahead and create it in the top module. Oh, actually, you know what? I want to do it a different way. I'm going to do it this way, just to show you guys an alternate way to go about doing things, right? Since we're still kind of creating modules, let's do this. Let's create our 5 to 32 decoder. Here, we're going to do it outside of the top module, and then we'll put it in the top module, and I'll show you kind of what that looks like here in a second. So we want to do module decoder 5 to 32, inputs A and D, and module. Let's go and take a look at our setup here. We've got 5 bits of A, 32 bits of output. The wire is 12 bits, remembering that we're going to connect it all in descending order, not ascending order like we've drawn it here. Okay, so input, this is 5 bits, so it should be 4 to 0. A, output, 4 to 0, so that's what, 32 bits, so 31 to 0. D, we need a wire, I already forgot how many bits, 12 bits, so that's going to be 11 to 0. W, and then our module instantiations. So what do we have? 3 to 8 and a 2 to 4. So a decoder 3 to 8, 2 to 4. And you might have noticed I like to do the bigger one first and then the smaller one. You don't have to do it that way. That's just the way I like to do it. So A takes the first 3 bits. So that's going to be 4, 3, 2. So that's going to take A, 4 to 2. And it's going to take the first 8 bits of W. So dot D is going to be attached to wire 11 down to what? Down to 4, I think. Let's try that. Now decoder 2 to 4, call that U1. Its dot A is going to be attached to A 1 and 0. That seems correct. Its dot D is going to be attached to wire 4 bits. Yeah, we got it right. 3 to 0. Drop that in. So we've got our module instantiations done correctly. Now our AND gates are equal to, so we'll start with assign D31 equal to, just like before, the top of A, so wire, top of the first one, so that's wire 11, and wire the top of the second one, 3. And then what we want to do here, since each one is going to go 3, 2, 1, 0, so I'm going to copy and paste that 3 more times, and I'm going to change it to 30, D29, D28. These are all going to be the 11, and it's going to be wire 2, 1, 0. Now it repeats there, so we'll go 11 down to 4. This is the big one. 11, 10, 9, 8, 7, 6, 5, 4. Oh, I should have put lines in between these. Hold on, I'm gonna do this. Just so it's a little bit easier to look at. And we go 10, 10, 10, 9, 9. Some aspects of Verilog programming are tedious, and there's really not a whole lot we can do about it. There are some structures that let you automate some of this, but they're a little bit tricky, so we're not going to worry about them right now. 6, where are we at? 5. 4. All right, now we should count down here. So 28, 27, 26, 25, 24, 23, 22, 21, 20, 19, 18, 17, 16, 16, 15, 14, 13, 12, 11, 10, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and 0. There we go. That was a monster, but we got it done. All 32 bits of output wired up the way they ought to be. So that is all there is to it for our 5 to 32 decoder. And now we need to test it. So, like we've been doing, I'm gonna grab this test bench. We'll create a new file, decoder 5 to 32 underscore tb.v. I'm gonna, oh, guess I didn't get the stuff I needed. Let's see. Copy, that's from the 1 to 2, we gotta remember that. So let's do Control F. 1 to 2 should become 5 to 32. Bam, all right. Now let's make sure we remember to fix our inputs and outputs. So that's a 4 to 0 and a 31 to 0 to make it 2 bits and 8 bits. Now let's go ahead and create our input. So A equals 5 bits. So we're going to do this in decimal now. 0 and delay for 20. Actually, since we have to do a bunch of these, I'm going to show you guys a trick. Let's do this instead. I'm going to create integer I equals 0. I'm going to go for I equals 0, I less than 32, I equals I plus 1. I think this is the syntax for this. I'm not 100% sure though, so this might not work. We might end up having to do it the hard way. Anyway, it's been a little while since I've done a for loop in Verilog. So now I think I can do A equals I and delay for 20. So that should do the thing. But I guess we're going to find out right now. So that should be everything that we need to do in order to do this test bench. So we're going to bring back PowerShell. We're going to clear. We're going to do I, Verilog, option O, decoder 5 to 32.vvp from decoder 5 to 32 underscore tb.v. No syntax errors. VVP decoder 5 to 32.vvp. Hey, look at that, it created the output file. Looks like our for loop may have worked. GTK wave. Grab GTK wave, file, open tabs. Grab our 5 to 32.vcd. Grab all of our stuff. I don't care about the integer, so I'm not gonna worry about it. And append. Oh, look at that. It would seem. Why is it so big? So it seems like, oh, I know what happened. We need to kind of zoom out a little bit to see everything. And this is in hex. So this is 32 bits of hex, so it makes it a little bit difficult to read, but I do think it appears it's working correctly. We've got 8, 4, 2, 1, 0, 8, 0, 4, 0, 2, 0, 1, 0, 0, 8, 0, 4, 0, 2, 0, 1, 0, 0, 8, 0, 4, 0, 2, 0, 1. Yeah, this is doing it. So we can kind of scroll down to the end and see that the last thing should have been all zeros and a 1. 2, 4, 8. 2, 4, 8. Yep, this guy is working correctly. I wonder how crazy it looks if we do it in binary. Oh yeah, it says like, look man, I can't show you everything. So we gotta like zoom in and scroll around to see what's going on. But here we go. This shows us that it's working properly. Ah, there we go. That's what I wanted to see. I wanted to double click on it. If it's too much, get out of here. Sometimes it kind of sucks to have to read all of that binary, but if we break it out, so all I did was double click on this signal, and we can see that what we want to see is that pulse, that 1, sort of forming this big long diagonal chain all the way down to the end. That lets us know that our signal is working correctly, and our 5 to 32 decoder is working properly. So that's great. We're done. There's one last thing to do, and that's going to be to put it in the top module. So now we're ready to undo the top. And so what we'll do here, we're leaving top exactly the same. We're going to create our inputs. 5 bits, so that's going to be 4 to 0, A. Output, 32 bits, so 31 to 0, D. And I'm just going to create my module here. I'm going to go decoder 5 to 32. I'm going to call it U0, A, and D. Cool. And that's all we need to do. A lot of times it's a good idea, a good best practice is in your top module, you really should have only inputs, outputs, module instantiations, and maybe wires to connect modules. But if you ever have logic happening, AND gates, OR gates, NOT gates, or anything like that, they probably need to be in a smaller module. But that's just sort of a good Verilog best practice. Let's go ahead and test it one last time. And we'll show you some other interesting things. So we'll call this one testbench.v, and I'm going to basically copy everything that was in that 5 to 32 decoder testbench. What are you at? There you are. So copy, test, and I'll show you guys a little inside baseball here. So this is going to be the same thing, except I need to change this to pick up top. But other than that, that's going to work. And this is, by the way, how we score your stuff. Integer, I'm going to call it score equals 32. So 32 possible test cases. And down here in the code here, I'm actually going to say if D does not equal, Ooh, this is going to be tricky. Okay, so here's the hard part, right? So D does not equal, but like, what do I put in there? I have to calculate, since I'm not doing it line by line, I'm doing it in the for loop, I need to get kind of creative. So I know this video is getting kind of long. If you're ready to check out now, feel free. This is just going to be kind of some interesting advanced stuff. What I think I can do is I can create a 32-bit register. So 32-bit register that I'm going to call check. And I'm going to instantiate it with 32 bits of hex, and it's going to be 8, 0, 0, 0, 0, 0, 0, 0, like we saw in the test bench. Now, as it turns out, in binary, when we divide by 2, we may have talked about this way back at the beginning of this semester. In binary, when we divide by 2, it does the same thing as shifting a bit to the right. So what I'm going to do is I'm going to say if is not equal to check, then score equals score minus 1, right? So it should pass that check. And then I'm going to say check is equal to check divided by 2. And this should shift the bit from left to right and keep the check where it needs to be. So finally, down here at the end, I'm going to display test ended with D. This is just a placeholder for the integer that we want to use. Tests passed out of 32, comma, and then the score. Provided I didn't screw anything up, this test bench should work and grade our assignment. So let's go to the PowerShell and let's clear everything out. So what I'm going to do, this is Verilog, option O, testbench.vvp from testbench.v. Hey, look at that, no errors. VVP, testbench.vvp. Little break. Hey, look at that. Test ended with 32 tests passed out of 32. Look at that. Just to sort of, I don't know, mess around. Let's see. I'm going to go and break something. Let's do this. Let's go back. I'm really excited that worked. Let's go back into our 5 to 32. And I'm just going to mess up this one. At line 41, I'm going to change it to wire 7 instead of wire 2. In test engineering, we call this the empty socket test, right? A lot of times in the testing class, if we have like, oh, look, the test works, and then you sort of pull the device out of the socket, and the test still works. We want to actually create a failure, right? We want to create an instance in which our test bench fails, so that we kind of have at least some confidence that our test bench is working correctly. So we did that change. We intentionally messed up our decoder. We do that, VVP, and look at that. Our test ended with 30 tests passed out of 32. So that gives us some confidence that our test bench is working, because we changed the output and got something that was messed up, and 2 of the test cases failed. Interesting that 2 of them failed, but I guess we'll see. So let's go ahead and close that out, and I think we are done. Let's make sure we go back and fix the thing that we screwed up. So that should be 9. Let's go back and run our test bench again. Look at that, 32 tests passed out of 32. So that looks good. I'm interested that it passed, that 2 of them failed. I feel like only one should fail since these are all tied to just one test case. But that's a exploration for another time, I suppose. So there we have it. That is the entire assignment from top to bottom. Looking at the timer, it took about an hour to get it done, which is not an insubstantial amount of time. But let's just kind of recap what happened here, right? We started with our assignment. We knew how we needed to compose our decoder, right? We knew that k was equal to 5, which is odd, which meant that we needed a 3 to 8 and a 2 to 4. And we saw kind of how we drew out how it should look. We noted where the wires should be and what they should be connected to. We noted how big the wire bus should be. We saw that we had 3 to 8, 2 to 4, so we kind of worked our design down all the way until we had just our 1 to 2 decoders. And then we went and implemented it in Verilog. We started at the very bottom, working on 1 to 2 decoders. We did a test bench for that 1 to 2 decoder. Remember, in that case, we found out that the bits were kind of flipped over, so we needed to flip over how we were representing our stuff to make it work where everything would be in descending order. We should have worked our way up the chain. We encountered syntax errors along the way. We read the errors. We went back to our code to fix the errors and see what went wrong. Hopefully, this kind of illustrates for you the entire design process. How do we go from the instructor said, make a thing that does this, to our working prototype down there at the very end. So this is the sort of design flow, the sort of philosophy that you can apply to the upcoming assignments. There we go. I think an hour is plenty. So as always, if you have any questions, comments, and concerns, either leave them in the comments for this video or post them up on our classroom on Microsoft Teams, so that way you guys are helping each other and I'm not just getting blasted with emails all day. Thank you so much, guys. Hang in there. I know this is difficult stuff, and we'll just keep working on it together, man. Thank you so much. I'll see you guys later. Bye.